Hello, welcome to the video. And until now, we saw resistors and capacitors in CMOS process. And now we will take a look at the MOS transistors or MOSFETs in the CMOS process. And we will see the MOS transistor modules, how they look in CMOS processes. So as we know, we have source, gate, and drain terminals. And along with that, there is a fourth terminal, which is a body terminal in our MOSFETs. So there are two types of MOSFETs, NMOS and PMOS. We know these from our basic analog electronics courses. So now we will just quickly revise it that we have a P substrate in which we have N dopants, and we have our polysilicon layer, which is our gate, and we have our source, gate, and drain terminal. Along with that, we also have a body terminal. And when we have two NMOS devices like these, we can see that the body is common to both of them, and we need to keep the body to drain and body to source junction reverse biased. So because drain and source can only make channel between themselves and not with the body, that's why we need to keep all the body to drain and body to source junction reverse biased. So body of the NMOS device is connected to the lowest voltage on the IC. And when it comes to a PMOS, so it's easy to make a PMOS. So we just make a N well, and doped P regions we have as our source and drain, and we put a polysilicon layer as a gate, and we have our body. And in case of PMOS, the body of PMOS is connected to the highest possible voltage on the IC. And there is also something known as triple well process, in which what we do is we have our N well. Inside that N well, we again make a P substrate well, and in that we make a NMOS by two N doped wells, and we put a polysilicon layer of our gate, and along with that we make a body which is separated within itself inside a N well. So this body is isolated with all other bodies of the transistors, and in this case we have a N well, and the body is isolated from other body on the IC, and this transition can be connected independently. And it behaves regardless of what happens to the main substrate. It is isolated completely, and the transistor is connected independently. So in this case, we need not to connect the body to the lowest potential, and we can connect to any required potential accordingly and according to our requirements. So let's come to the large signal model of our MOSFET. So we represent our MOSFET like this. We know this already. So we have our high potential terminal as our drain, low potential terminal as our source, and we have our gate. So between gate and source, VGS is formed between, and we also have our body. So between drain and source, we have VDS. Between body and source, we have VBS. And when a voltage greater than VT is applied at gate, current ID flows through drain to the source. So the MOSFET is symmetrical, and the higher voltage terminal is the drain, and lower one is source. So ID is basically given by mu n, which is mobility, times Cox divided by 2 times omega by L multiplied by VGS minus VT square multiplied by 1 plus lambda VDS. And this factor is very less, and that thus the whole factor is very close to 1. It's almost 1. And this current follows the square law model. And this is when our VGS is greater than VT. We'll shortly discuss the working as well. And our VDS is greater than VGS minus VT, which is our saturation region. And when our VGS is greater than VT, and the VDS is lesser than VGS minus VT, then what happens is I naught does not follow the square law model, but it changes its equation to something like this, and this is which behaves like an exponential curve and does not follow the square law model. And this is called our triode region. This is the behavior of our current in triode region. And when VGS is less than VT, so at that time our ID is 0. So if the gate voltage is less than the threshold voltage, we have no current in our MOSFET. So if we plot a ID or drain current versus the VGS curve, so initially there is a asymptotic incremental and it goes rising exponentially after VT. So till VT, we say that there is almost zero current, and after VT we have an exponential growth of current. And similarly, if we plot ID versus VDS, so we get different. So we get the curve like this, which is this is a triode region and this is the saturation region, and for different values of VGS we have different values of currents. So this is how the curve looks, and the MOSFET can be used as a resistor when operated in a triode region, so basically this region, and in deep triode region over here something, it will act as a switch. So VT is a function of voltage between source and body, and VSB is nothing but minus of VBS, which is why VT equals to, we can say that VT is a function of VSB, and the relation between VSB and VT is given by this equation. And this VT naught is a standard VT where VSB is actually 0. So now we will discuss about the saturation and triode boundary, which is roughly this boundary. And we have a structure of our NMOS device, and if we connect the drain and source together, means they are at the same potential. So if we connect them together, so let's say they are at same potential, then now what we do is, when we go on increasing the potential at gate, so what will happen is a depletion layer will form, and which is between drain and source. There is a inversion layer which will be formed, and this inversion layer between drain and source is responsible for the flow of the current. And when the potential at gate is greater than VT, the inversion layer will form. So due to the inversion layer around drain and source, there is also a depletion layer. So when drain and source are at same potential, the amount of voltage required at gate to form an inversion layer is called threshold voltage, and it is given by threshold voltage is VGD or VGS in this case, because drain and source are at same potential. So now let's say drain and source are not at same potential. So drain is at higher potential and source is at lower potential. So let's take a case where VD is greater than VS. So basically at this point what happens is, the inversion layer will be thicker at the source side. So basically, for saturation, we said that VDS must be greater than VGS minus VT, or VG minus VT should be lesser than VD. So what happens actually is, we can rewrite the equation as VG minus VD should be lesser than VT. So means the drain to gate voltage is not more than VT, and it shows us that the result is, drain end is not having any inversion, but source end is having kind of inversion. So the inversion looks like this, and at the drain junction there is almost no inversion, and at source junction there is greater amount of inversion, and the channel is pinched off at the drain. So this is the terminology we use in CMOS processes, where we call it as pinching off when the voltage at drain is greater than the voltage at source. So in triode region, even though voltage at drain is greater than voltage of source, so basically what we talked about here is related to the saturated region. But when talking about the triode region, uh, even though the drain voltage is greater than the source voltage, but VDS is always less than VGS minus VT, and that's how we say that our working is in triode region, and we do not have inversion at drain as well as gate. So but the inversion at source end is greater than the inversion at drain end, and when VDS, so basically drain to source, is 0, means we say that drain and source are at same potential, VD equals to VS, then there is a uniform inversion as we expected. So this tells us that once the drain end is pinched off, the drain will not have a significant effect on the amount of charge in the channel, and thus we get the constant current in the saturation region, and we say that in saturation region the current does not increases significantly. So we can like almost we can say that it's almost constant. So now we will see the effect of source to the body voltage. So we have our body terminal as well, and this is our channel, and on this channel there is a polysilicon gate. So we have a capacitor between gate and the channel, and there is a dielectric which whose thickness is T of ox. So there is a dielectric of metal oxide, and the thickness is T ox. So as a voltage is given at the gate terminal, if for example, like let's say if we raise the voltage across the capacitor, so these both sentences mean the same meaning. So basically, between gate and the channel there is a capacitor, and we increase the voltage at gate. Basically, if we increase the voltage across the capacitor, the charges are formed below the channels over here, which is our inversion layer, and which is called the inversion layer, and is used for conduction of a current. So if we observe properly, there is one more capacitor found between the body and the channel across the depletion layer. So this depletion layer acts as the dielectric, and between the body and the channel there is one more capacitor. We can see it, and so we can consider this as a channel, and from gate to the channel we have Cox, and from channel to the body we have capacitance due to the depletion layer. So Cox is nothing but epsilon ox divided by the thickness of the oxide, which is Tox. And clearly, if we increase the voltage at gate or body, the channel charge will be influenced in the same way. So as we increase the body voltage, or as we increase the gate voltage, more charges will be deployed at the channel, allowing it for more conductance. And thus the body is also called as the back gate, and in many circuits it is used as a gate as well. So now we will look at the width and the length of the MOSFET. So basically, if we see structure of MOSFET in this way, so this is what the length of the MOSFET is, and if we look at the top view of this device from the top, so we have the structure something like this, which we have the drain and sources, and we have the gate, and thus we can get the width and the length. So if we plot it in the 3 dimension, so we can say that this is our drain and sources, and this is our gate. So basically this is our width of the MOSFET, and this is our length of the gate, basically, which is a length of the MOSFET. And now it turns out that if we double the width, it's like connecting two MOSFETs in parallel. So imagine two identical MOSFETs with same VDS, VGS, and VBS, and when we put them next to each other, then current through them just adds up. So ID, or the current through the MOSFET, is directly proportional to width. And from this equation of ID in triode region, and we know the dependency of VT on VBS, as VSB increases, the current effect due to the body decreases, and as VBS increases, the current effect due to body increases, as VSB is minus of VBS, and we definitely don't want and thus we definitely don't want our effect due to the body to increase. So we definitely don't want VBS to be increased, and thus we keep it in a reverse bias condition always by attaching the body terminal to the lowest potential of the IC. And now from the equation of ID, we know that ID is directly proportional to the width, and ID is inversely proportional to the length from this equation. But so basically, we can say that ID is directly proportional to width, and which is somewhat accurate. But the dependency of ID or the proportionality of ID with L is inverse, and this depends on some complicated factors and some restrictive conditions because the field in the MOSFET is reduced if L is increased. Also, there are lots of non-ideal effects which make ID not exactly inversely proportional to the length of the device. So let's take an example of current mirror. So we know the structure of current mirror, and we have our I naught flowing through this transistor, and we want from this MOSFET we want 2 I naught. So if we want 2 I naught, then we always scale the width and not the length of the MOSFET, and this we'll see more in more detail in upcoming slides. So before that, let's cover the PMOS transistor as well. So the PMOS transistor has a same but opposite structure where the source is connected at the potential, and we have a I naught from source to drain, and we have between source and gate we have VSG, between source and body we have VSB, and we have VSD between source and drain. And this can be presented in such manner where we have our P structure, we dig a N well, and we have P doped P regions, and we have our source, gate, and drains, and we also have our body. So the current is given by this equation, which obeys a square law model, and where VSD should be greater than VSG minus VTP for our saturation condition. And for our triode region, ID is dependent on this equation where VSD should be less than VG minus VT. So basically when VSD is less than VG minus VT, we have a triode region. So now in NMOS devices, VDS must be greater than VGS minus VT, and in PMOS devices, VSD must be greater than VSG minus VT, or we can say that minus of VD must be greater than minus of VG minus of VT. So basically this means that VD should be less than VG plus VT. Over here in NMOS, VD should be greater than VG minus VT. So these are some conditions which must be satisfied, as we always want our MOSFETs to be in saturated region. And now as we said that we need our VGS to be greater than VT for the current to flow. But in reality, that's not the exact case, and that's where the topic of subthreshold operation comes in picture. So the phenomena of VSG greater than VT, basically for PMOS, or in case of NMOS, VGS greater than VT is called the strong inversion or the saturation region. And ID is basically some value of K, which is constant, which we look over here. This is some constant, and ID is equals to K times VGS minus VT square according to the square law model. But when this voltage drops below the VT, in reality, ID does not becomes zero. So when VGS is less than VT, ID is some exponential value, and which is I naught exponential of VGS divided by N or neta VT, where this VT is a thermal voltage, and which is basically 25.9 millivolts at 300 Kelvin or room temperature. So I think that's all for today's video, and thank you for watching.